One way to have a viable idea is, as in any Poisson process, it just drops in your head at time t. The other way to have a viable idea is suddenly the cost threshold has changed, and an idea that you had 6 months ago that was not viable with the cost threshold 6 months ago is viable today because the cost threshold has changed. Okay, so there are two ways to have a viable idea. So let me show you about the stochastic process. So don't actually pay attention to the stochastic process, but do pay attention to this diagram. So what I have drawn here is an arbitrary cost threshold. This is a function c of t. So here's time, and this function is the cost threshold. And the idea here is if the recipients of ideas were not banking the ideas, then if you had an idea at this point in time, you would accept the idea if it were lower than the point on the curve, and you would throw it away if it were higher. But now let's suppose that you have an idea, and it's here, it's higher than the curve. So you're not going to throw it away, you're going to put it in your pocket. When does that matter? So if you put it in your pocket here, and the cost threshold is falling like this, and if the cost threshold were falling forever, that idea that is not viable here is never going to be viable because the cost threshold is only becoming more stringent. So if it's not viable at t, it'll never be viable. However, suppose you have this idea here at t1, and at some point the cost threshold starts to rise. At some point, or say take the one I've drawn here, this one with the dotted line just here. That idea is not going to be viable. It's not viable here, not viable here, not viable here, but bingo, when you arrive at T2, suddenly it is viable, and suddenly, even if nobody has an idea there, your idea becomes a viable idea and the game stops. So that defines a different stochastic process than the one that I described before, and a rather complicated stochastic process described recursively by this expression. So by recursively, I mean you can describe this stochastic process differently on the increasing part of the cost function and the decreasing part of the cost function. That's what we do, and for the reason I just gave. And you define it recursively by referring back to some cumulative probability that came before. But don't pay attention to that. The only reason I mention that is that if you ever find yourself doing this problem, it took us a while to come to this conclusion to describe the stochastic process. So this is how you do it if you ever need it. Okay. What's remarkable about this, so it turns out that in this model where you can bank the ideas rather than just throwing away the ones that you don't want, it turns out that really for the same intuitive reason, the value function is still declining. So it turns out that even though the value of this game, the value of this decision problem will be higher because essentially you have access to ideas that you didn't have before, and in some average sense that means that you're making better use of the ideas. So the value function will be larger than it was when you throw unused ideas away. But the value function is still declining. And what that means is it's still going to be true that in the optimal policy, the optimal cost threshold is increasing. Okay, so the threshold that the planner wants to implement will still be increasing. He's still going to become more and more and more lenient about bearing cost as time goes on because the distribution on lambda is becoming more pessimistic. Okay. It will be monotonic. Yes. So we did all this work apparently for nothing, but unfortunately, unfortunately, so here's how the proof goes. The way it was not for nothing because the proof that C is monotonic is indirect through the proof that the V tilde is decreasing. And we prove something much stronger than we need in order, you can't start with the belief that the C is monotonic, so you have to prove that the V is decreasing for an arbitrary C. And because of that, we had to deal with this stochastic process. Okay. Okay, so now the question is, so I started by deriving the optimal cost threshold that the planner would like to implement. And the question is, can he implement it? It turns out that in the case that ideas that are not used are discarded, it's extremely trivial to implement the optimal cost threshold. So what is the policy available to the planner? So the policy available to the planner is he chooses a reward function, this rho function, sorry, which is also a function on time, which states at each point in time what is the reward that the inventor gets if he fills the market niche at that point in time. Okay. If every idea, if the only idea, if you are unlikely to get more than one idea, the only idea that you will ever get is the one you got just now, and you can't keep the idea for the future, your only decision is to invest in it right now or not to invest at all, then the only question you face is whether or not the reward is greater than the cost. So it's extremely easy to implement the optimal cost threshold in the case that unused ideas are discarded. You just set the rho equal to the C, and that will do it. And the only thing that teaches you, which I think is very intuitive and of some interest, what that teaches us is that as time goes on and the market niche isn't filled, the reward that should be offered, however it is offered, notice that this is completely agnostic on whether the rewards come from intellectual property or from some prize system or from some government sponsorship or whatever. It's agnostic on that. Whatever the reward system is, what this is telling us is that as time goes on, the reward should be increasing, okay, because the optimal cost threshold is increasing. However, now suppose that ideas can be banked. Okay, so still the social planner has to choose the rho. How is the problem different if the ideas can be banked? So now, okay, so let me just skip past this. So I just said this. Implementation is easy in the use it or lose it model, but it's not going to be easy in the use it or bank it model. And why is that? So suppose we try the same trick. Okay, so suppose we try the same trick of setting rho of t, the reward, equal to the cost threshold at each t. Now, suppose that you're somebody who has the marginal idea at time t. You have the marginal idea. Your idea has a cost of c of t. Okay. Now ask yourself the question whether you, as the recipient of this marginal idea, c of t, ask yourself, would you invest in this marginal idea as is intended by the social planner, because the social planner is trying to implement c of t, right? Social planner wants you to invest if your idea has cost c of t or less. Would you invest? And I contend you wouldn't. If the cost threshold is increasing and the reward threshold is therefore, the reward is therefore increasing, surely if you're going to make zero profit by investing right now at cost c of t, surely you're willing to gamble on waiting for some period of time and investing later when the cost, hence the reward, is greater, because even though you may be preempted, at least that's positive profit. So you can no longer implement the desired cost threshold by setting the reward equal to the cost. And the question then becomes, what do you do instead? How do you have to set the reward? Okay, so this then becomes an implementation problem. What is it, how does the individual behave, and what does the planner have to know about the individuals in order to manipulate their behavior so that he implements the optimal cost threshold? And can he do that, and what does this rho function look like? Well, there's one thing we know about it immediately. We don't have to think about it. The rho function has to be larger, strictly larger than the cost threshold. So at each t, the reward has to be larger than the cost threshold, because otherwise you're just going to wait for positive profit sometime. You're not going to accept ever a negative profit. And if there's ever an opportunity for positive profit, you're just going to bank the idea and wait. So that we know. But frankly, that's not very much to know. The question is, what does he do?